Okay. So last week we went over linear regression, and I think, as I told you last week, it's a good like baseline or foundation for what we'll be learning in the rest of class. And so if we remember, like linear regression is like kind of this method of finding a straight line that like best fits a set of points. And so last week we made a data set, a random one, and then we like tried to make a best fit line by changing like the weights and the biases such that it would, look something like we have, or make like a best fit line essentially. And so we compare that to kind of what it really is, which is training. And then we went over like loss, which is essentially our error. And then we built a function down here that would calculate the loss. So here we did mean squared error. So yeah. And then we talked about one way that computers can minimize loss, which is through gradient descent. Can anyone explain what gradient descent is? If you remember.
I think that like gradient descent is like is like where the computer itself like it tries to like I don't know, it seems like it looks like well it like identifies a point and that sees like if you like I don't know like suppose it's like somewhere on that parabola which is show and then it'll like try to change its weight or something and if it sees that like, by that changing will it go down or not?
Yeah. That's pretty good. So essentially, if you remember, like we find a starting point on the curve. This is our loss curve. It's like the value of the weight, since there's so many values that you could choose. And we always know that there's a specific weight like value where the loss will be minimized. So here it's like somewhere down here, but we don't really know where that is. And we want like that specific value, since we know that if our weight of our loss is minimized, then that would be the best possible model that we could get. So to do that, we just start at a random point and we like calculate the slope at that value, which we also call gradient. And then we step down like this curve until we reach the bottom or the minimum. How much we step by is really important. That's what we call our learning rate. And so having a small learning rate means that will have very small steps, and it might take forever to get to the bottom, but we'll get there eventually. But if we I guess if we have I didn't change this, but if we have a very long uh like a very large learning rate, we'll end up stepping over the bottom or the minimum of the loss curve. So finding like the perfect learning rate or the Goldilocks number would mean that we'll get there efficiently to the bottom of the loss curve. And so your homework was to finish these 4 questions. So yeah. And that was kind of like tuning hyperparameters, which is what we're going to do today. So if you would like, you can open up, I think it should be in your Google Classroom. It should be week 3. It's called Introduction to TensorFlow.
Do we have any like of these collab things for today? Because I couldn't see any.
It should be there.
Oh, really?
Hopefully, classwork right there.
Okay, so mm, oh, okay, so it's the no due date one, right? But we still have to finish it.
Yeah.
Okay.
Cool. I'll give a couple more minutes for everyone to get in. Okay, let's get started. So today I want to introduce you to TensorFlow, which is the machine learning package we'll be using in Python. And that'll be kind of the basis of everything that we're going to learn from here on out, which is a little daunting, but I think we'll all be able to do it. So, so with that, we'll be learning the basics of NumPy and pandas, which are some I guess fundamentals that we should learn as well. Use our previous knowledge on linear regression, evaluate those loss curves, and tune hyperparameters like you did last week. So here's kind of what TensorFlow would look like. So it's a machine learning package, and oftentimes machine learning can be a very complex and kind of daunting subject, which is probably why you guys are taking this class. But in TensorFlow, it's kind of broken up into different things. So you have this low level TensorFlow functions near the bottom, which provide extensive control of your computer. But what we'll be doing is we'll be using some of those high level, more abstract functions, and hopefully are a little bit more readable or more helpful to understand. So yeah, we'll be doing the easy stuff.
For some reason, when I click it, the Your Work section isn't loading, so I can't actually get into the collab.
What do you mean? Your work?
I can't click the link because it's not loading. It's
Can you try doing it again? I'm not really sure how it.
okay.
Is it it just doesn't load at all?
Yeah, it just doesn't load. I already reloaded the page a few times and I've waited, but it's just not loading.
Does anyone else have that problem? Or
mine is working totally fine.
okay.
I guess I'll just watch the recording or I'll catch up on it later.
Okay.
Yeah.
Yeah, sorry about that. I'm not really sure what the problem would be. Maybe you could try trying going on a different computer. Maybe that's the problem.
Okay.
I think you still have the link to the Zoom, right? So you can go on another computer and just rejoin.
All right. I'll just figure that out.
Cool. Okay. So yeah, TensorFlow, it's a machine learning package, and we'll be using it. But I guess we should also learn some basics. So we're going to learn some NumPy, which is, if you remember from last class, is one of the ways that we coded our mean squared loss, especially this second implementation. And so although we won't be necessarily using the functions in here, we'll definitely understand how this code works. So first what we need to do is we need to first import NumPy, which is a package, and it should be pre-installed on the Colab. And so all the functions under NumPy will be under this like banner called like mp dot, and then you get a bunch of functions under that you can use. And if you notice, a lot of these are mathematical functions because NumPy is the mathematical package for Python. So one of the most helpful functions that NumPy gives us is the NumPy array or matrix, which allows us to create NumPy arrays that we could use in our own math. And so these are different from lists that we learned in normal Python. So if you see them right here, like these aren't lists, but they're another type called a NumPy array. And so when we call these, you can't do like the normal things with like a NumPy array. I mean, with a list, but yeah, they're different. So if you call an array like this, you can see that it prints out like the values that you put into the list. So it works in that kind of way. But you can also create like two-dimensional matrices. So like here, you have like lists inside of a list, right? And so this is two-dimensional. So you print that, you get like a two-dimensional array. Or like, yeah. And so if you wanted to create a matrix of zeros, so if you wanted to do like a matrix of all zeros, you could call it mp.zeros and say like 8. And so if you print that out, you get a list of zeros. You get a list of 8 zeros. Or you could do ones like this and get a list of 8 ones.
So if you type in the number plus like plural form, then it's just like built in and it does that?
Yeah, I mean, so it's only for ones and zeros, since like I guess those are the most like useful.
Oh,
But you
okay.
can't like do twos. I don't think twos is a thing. Yeah, like twos is not things, but ones and zeros is a thing. And then you can also do like, remember range? There's also a thing in NumPy for range, which is called a range. So this would create a NumPy array that goes from 5 to 11. So if you print that out,
So what
we go
does
from
like
5 to 11.
what does a 2D array do?
So a 2D array is like, it's like kind of a matrix, right? If you think about it, it's like,
So it goes on like different lines? Is that
yeah. So
okay?
it's just like a way of like organizing numbers. If you know, I think the most common like organization of like a image, like a picture on a picture is like a 2D array of pixels, right? So you
Yeah.
have like pixels going left, like to your
Okay.
right, and pixels going down.
Okay.
And that's
Yeah.
kind of a two-dimensional array of pixels.
Right. I mean, like, is there such thing as a 3D array? It doesn't really make sense for it to exist, but like, is it technically a thing?
Yeah, there is. So like, we can go back to the image example. Every pixel in your computer has a combination of like red, green, and blue color values, right?
Yeah.
So like, you have that two-dimensional array of pixels, and then each pixel has 3 values inside of it, which creates a three-dimensional array.
Oh, okay.
So that's one example of a three-dimensional array. And I can't really think of a concrete example of a four-dimensional array since we're kind of in a three-dimensional space. But yeah, that's a good question. So yeah, we can populate arrays with random numbers. So there's like this thing where you can like create random integers into an array. So this is one of them. So like we can create random integers between 50 and 100. So by telling the low is 50, the maximum we want is 101, and the size of our array will be 6. So we create 6 values between 50 and 100. So yeah. And if you simply want a bunch of values between like 0 and 1, you can use numpy.random.random and then print them out like that. And I don't expect you to memorize any of these, since one of the, I guess the key things about programming is that you can search documentation for NumPy, which is really helpful. Yeah, you can like search like NumPy documentation into your computer, and then you can get like a list of all the functions that NumPy has available to you. The next thing that we should learn is really like the key to why we would use a NumPy array over lists. So if you kind of remember back here, it was really easy to just subtract two lists or two NumPy arrays, right? If you remember back here, like if we looked at our other solution, we had to use like a whole like for loop inside of a function, but here we could just subtract the two, and it just did it for us. That's one of the strengths of NumPy, where it has like these built-in mathematical functions for us. So if you want, what you could do is you could just use, so we created a list of random values here, and just by doing like a list plus an integer, we can add like 2 to every single value in this list, just automatically. And that's a thing called broadcasting, where even though like the types are mismatched, it'll like try and solve it for you. So like, so even though, so like this is a list and this is an integer, and normally you can't add those, but NumPy will try and do it for you. And if it can't figure it out, it'll throw an error. But in these special cases, like a list and an integer, or like you can like multiply them even, I think. Like you can see how it like does it for you. So there's that kind of stuff. So yeah. So remember like this thing, you can like multiply them as well.
What about stuff like strings and you tried to add a string to the end of it?
I mean, we could try. It's like, I think this would fail, but we can try it anyways. Yeah. So, yeah, so you can see like this error right here.
Okay.
Like function add did not contain a loop with signature matching types. So if
like
you wanted to
floats
sort
and
of like
integers
kind of decode what this is saying,
Okay.
huh?
So like floats and integers can kind of add together because they're both numbers and the computer can just figure it out.
Yeah. But here it doesn't understand like how do you add a string and a number, right?
Yeah, okay.
So just to kind of use what we've learned, let's try and make like a linear data set. Kind of what I did for you last week, but we can like try doing it our own. So here it's Your goal is to create a simple data set consisting of a single feature and a label as follows. And so assign a sequence of integers from 60 to 6 to 20 inclusive to a NumPy array named feature. And then also assign 15 values to a NumPy array named label, such that label equals, it's right there. And so like do it in, you can like write your code right here. Like replace the question mark with your code. And so everything you need to do this is like right up here if you just like forgot what we were doing. And if you're really stuck, like you can't do it, you can like click on this, but don't do that right now. And when you're done, maybe you could like type in chat maybe, or I don't know if you can like raise your hand, if that's a thing. Okay. Okay. So if you want to do this, we could use if you remember, we could use the arrange function. So if you want to go from 6 to 20, we go from 6, since it's inclusive, and then 20. So we want to go 1 above 20, since we want 20 inclusive, so 21. And then for our label, it wants to be 3 times plus 4. So we can do 3 times feature plus 4. And I hope PEMDAS does the thing for us. So yeah. So yeah, it works like that. That should be right. Yeah, 7 times 3 is 21 plus 4 is 25. Okay, yeah. So that's kind of what you might do. You can check the solution, see that, yeah, they kind of just did what we did, except they added like the parentheses to make it so, yeah. And then kind of to make it more realistic is like, this is like a straight line essentially, right? But if you wanted to make it more realistic, you would have to add noise, which is kind of like random values to it. So that's what you can do here. Try and make some noise between -2 and 2. Okay, so here I think it's np.random. I think it's randint, and you put low as -2, and then the high is 3, and then we have and this should be, the size is 15, I think. And then we can add, we can add label plus noise. Do that work? Oh no. Actually, let's see what this says. Okay. I guess that works. So here it wants and then what's 15, right? And then you just want to add like that. So this creates like 15 values from 0 to 1. And then we increase all of those we increase like this, the range from 0 to 1 to 0 to 4 by multiplying by 4. And then we shift the range down by 2, which means that our lowest value goes from 0 to -2. And then our upper value goes from 4 to 2, which is kind of how it works. So that's what this is. Is running that, we get our noise. So yeah, that's kind of what you would want to learn, or I guess that's what we want to know for now. The other thing we should learn about is pandas. So pandas, kind of like the animal, like the bear. Yeah. It's another package in Python, and it's our central like data structure that all kind of machine learning uses. And so a data frame is like that data structure that like the Pandas API uses. And it's essentially an Excel spreadsheet. Does everyone know what an Excel spreadsheet is? I can probably open one up. Excel. Yeah, okay. So like, so Sankrit says he knows what an Excel spreadsheet is, but he doesn't know what a CSV is. A CSV is like the same thing, except it's like kind of textual. Essentially means that every cell is separated by commas. That's what it stands for, comma separated values, CSV. And so data frames have stores like data in cells, and it has columns and numbered rows that you can like look at. So what we want to do next is import our stuffs. So NumPy is NP, like before, and pandas as PD. And so this next code will create like our data frame. So we have 10 cells organized into 5 rows and 2 columns, and we name them temperature and activity. And so this is our data, and it's a 5x2 NumPy array. And you can put those into a data frame. If you have the columns and you have the data, put them into a data frame, and you can print those out into a really pretty like 2D array, like that. So yeah, you can add columns to this data frame as well. So you can take like the activity column and add 2 to every value in it and put that into a new adjusted column, which is kind of how it works here. So now you have adjusted, and then you have everything in adjusted is +2 of what's in activity. So that's how that would work. Kind of like how, if you remember how you did lists, right? You do like list index that gets you the value at that index. You can get the column of a data frame by like putting the name of the column in these square brackets. And so there's just like a ton of different ways you could like look at a data frame as well. So you could get like rows 0, 1, and 2 by using dataframe.head. You could get row 2 by using a specific function called iloc, which would give you the integer location at 2. You could get rows 1, 2, and 3 by using the list splicing thing. Or you could get the temperature column itself by asking for temperature within these square brackets. And you can see like there's just like a bunch of ways to subset this data frame. And so our next task is to create a 3x4 pandas data frame with the columns Eleanor, Chidi, Tahani, and Jason, and populate each of the 12 cells with random integers between 0 and 100. And so, yeah. And then you want to print out the data frame and the value at cell run, like the cell of row 1 in the Eleanor column. And then a 5th column called Janet, which is the sum of Tahani and Jason. And you can put that right here. And so I'll be doing it at the same time if you get lost. Okay, so that's kind of how you do it. We have data, we make a data frame, we can print it out simply like that. We can get the value of row 1 in the Eleanor column by calling Eleanor, like getting the column and getting the first value in that column. And you can create the new Janet column by adding the Jason column and the Tahani column. Does the solution want? Okay, I guess that also kind of works. So this solution does it a little differently, where it uses the randint from the NumPy that we learned before. So you could kind of do the same thing. We have size 3 by 4, like a 3 by 4 matrix, and it'll create like the data for you. So it's kind of the same thing, I guess. So yeah. So yeah, those are kind of the two things that we should know for now. And then, okay, we'll skip this. We're not doing that. I think the main thing to realize there is that if you've ever worked with objects, Carol says, if we were to make, okay, Julia, can you make, give me a second, sorry. Okay. I guess we're going to skip this for now, but if you wanted to like duplicate a data frame, you could like assign a data frame to a new variable. The only problem there is that like if you're not actually like copying the data, you're just like adding a new reference to already existing data. The only way to like really copy a data frame is to use the data frame like copy method, which will create an actually independent copy. Yeah, but that's not super important. So what we'll do now is we'll get into TensorFlow, which is, I guess, we're trying to learn in the first place. So what we need to do is we need to import everything. So we have pandas as PD, TensorFlow as TF, and then our plotting package, which we're not going to learn since it's like beyond the scope. So you gotta run that. And then next what we're going to do is define functions to build and train a model, and just like run it. It's not super important to understand like what it does for now, but you can look at it if you want. And then we also want to get our plotting function as well. So you can run that as well. So, okay, so let's look at our data set. So we have our features, which is a list of numbers like last time, and then a corresponding list of labels. So these are like the X values and this is the Y values. And so as part of learning, as part of training, rather, we have our learning rate, which we had from last week, and two new values that we call epochs and batch size. And we'll use these three hyperparameters to train our model and then plot our loss curve. So just for now, I want you to run it. Oh, my feature is not defined. Oh, I didn't run this. So you got to run that and then run this. And then it'll go through the whole thing in this very fancy thing. So here. So you can see that this is our linear regression curve, remember? So we have like the values, like the dots, and this is our best fit line that our model is trying to make or has made. And it's clear that this is really bad, right? And then this is our loss curve as well. So over time as we train, we should see that our loss should go down, and it does. We want it to go even more down. So let's see. So our next task is I want you to increase the number of epochs. So that's changing this value, it's called epochs, and see what happens. Right here. You don't have to do it up there, do it here. So what happens? And does it converge? So, type in chat if it does, or it doesn't. So convergence means that our training loss, or this thing right here, is flat. Means that it can't get any better. We found the bottom of the loss curve. So yeah. What do you guys see when you increase the number of epochs from 10 to maybe 20 or 30 or 50? What happens?
What is an epoch, though?
Yeah. That's a good question. It's the amount of times that the model looks over all the data. So like the best analogy I could give it to you is like if you were learning to look at bananas, like you were trying to identify bananas, maybe you'd want to look at a lot of bananas a lot of times. And if you look over like your same data set a lot, you can like reinforce learning. So that's what the epochs are. It's the amount of times that you look over the data set, like the entire data set. Okay. So let's put in like, I don't know, 50. That's what happens. And so you can now see like, hey, this is a much better line than what we had before, right? But it still isn't, perfect, right? And our loss has like decreased significantly from like 18.
The higher it is, the better. But then, like, if you have a learning rate, oh wait, no, we're not doing a learning rate. We're doing epoch. What happens if you
Yeah.
type something like 1,000?
Yeah. So that's the thing, right? If you have a lot of epochs, you'll get there, right? But it will take like a really long time, like because you have to wait for it to finish. So like, oh, this is 50, right? And it took like 10 seconds. If I put in 1,000, you might be sitting here for 2 minutes, which on the grand scale doesn't seem like a lot. Well, let's say, what if one epoch took an hour? And you're like, let's put in 1,000 epochs. That's 1,000 hours, I guess, right? So there's like a delicate balance of where you need to put these to make sure that you're still being efficient. And so we still haven't converged, right? We still haven't found like this line still doesn't like follow up with the dots here. Although it did get closer. So next thing we're going to try is we're going to try increasing our learning rate. So let's look at this. So you can just run it. So this takes a lot longer. So yeah, look. So what do you guys notice when you look at these two graphs?
The second one looks like it has a lot of fluxes on it. Then it kind of gets narrow as it goes. Like
Oh.
if you learn a string instrument, kind of feels like when you first learn vibrato, you slide your finger up and down, and then you like stick, and then you like shorten, reduce the distance of like how much you move it. Your finger around it just kind of feels like that to me.
Mm-hmm.
I mean, like, I think, wait, what was the difference on this one then from the last one?
So in this one, we had a really high learning rate,
Oh,
and we
okay.
had like 500 epochs. So our learning rate was 100 compared to like, I think this one was like 0.01.
Yeah, so like last time when we did the homework and we tried to use that graph thing, you told us to use like a learning rate of 1, and it never got anywhere because it just kept on going from one side to the other.
Mm-hmm.
So I guess it's kind of like that, except since it's not perfectly 1, it makes some progress eventually.
Yeah. So like that's the thing here, right? As well. Kind of like you said with the vibrato thing, it oscillates, like the loss oscillates from like high to low, which really isn't what we want to do. And that's like that suggests that our learning rate is too high. And even worse than that, we can see that our best fit line is just way off. Like it goes from like, yeah.
Mean squared error stays at about 500.
Actually, our training loss is right there. It's
Oh, okay.
170,000.
Okay.
But yeah. And that's also a root, so it's also taking the square root. So let's try to find our optimal. So I'm going to try this as well. I'm going to try and find the optimal one as well. And I want you guys to do it as well. And when you think you found like a really good set of values, like type it in chat. It's not like competition or anything, but Okay.
if you do something like 0.5, doesn't it end up like perfectly in the middle, like that thing you showed us? The homework thing you showed us last time? Where the learning rate was like 0.5.
Wait, what do you mean? Like,
When you told us last time on the homework to test out how big we should make the learning rate to effectively reach like the center, the lowest loss, I guess,
mhm.
0.5 did that perfectly, except this time, I don't know. Would 0.5 be better? Like, does it matter depending on what the graph looks like?
Yeah, that's kind of what it is. It matters based on what the data is. That's like the thing. Each problem that you're introduced to in machine learning is unique, so you need unique hyperparameters for all of them. So there is no one and done perfect learning rate for all problems. You need to tune it for the problem you have at hand. I think Justin put something in chat. But he says, if you have 5 epochs, why is having an insane learning rate bad? So even with 5 epochs, so even having a very high like learning rate could mean that you would skip over like the bottom of your loss curve, right? You'd skip over like the perfect weight at the bottom. But there are cases where if you can only train for 5 epochs, maybe you would want to have a higher learning rate than normal. So what like Carol did is she tried, well, she texted this to me personally, but she says that she tried 0.5 and 15, which compared to mine, which is 0.2 and 50, she had a higher learning rate, but she had less epochs, which is kind of why it kind of maybe it like mellowed out the two. That's kind of why, kind of how it might work. So if you want to converge really fast, you would have to have a higher learning rate.
So if you're
Yeah.
trying to get robots to be able to like find the best, try to find the lowest loss, and you have to code it differently for every situation, then what's the point? And why can't people just like do it themselves if you have to code the robot every time to do it anyway?
I think my answer to your question would be computers are really good at finding patterns that even humans are really bad at finding. So the benefit to having the computer do everything for you while you just have to tune the parameters is that the computer is doing the hard work for you. You're just changing numbers. So even though like
if you
it
want
might seem like you're never like, you can't really solve the problem and do it one and done. In the end, you're just changing numbers. So it's not super hard, I guess. But yeah. So yeah, so I said 0.2 and 50. And the line is pretty good. You can see that our loss goes way down to 0 and it converges since the line at the bottom is flat. And so we converge at about 20. So what I could do even here right now is probably say like 25, and we could still probably get the same thing. Yeah. So you can see that we converged around 15 maybe. So yeah, I didn't have to train for 25. I can do even less than that.
So sometimes, wait, that's worse than before, but it took shorter, right? Like slightly worse, or no?
No, it's the same.
Oh, it is? Like,
Yeah.
it converged at a later time, though? Does that mean anything or no?
No. So if I so when I have a learning rate of 0.2, it converges at around epoch 15. So it doesn't matter whether I do 25 or 50 here.
Oh, okay.
It'll converge at at 15.
Oh.
That's kind of what it does right there. So if I do 15 here. Actually, actually, it actually hasn't converged yet. So I think it's 20 maybe. Yeah. It converges somewhere. Okay. So the next hyperparameter that we want to tune is what we call batch size. And so this is actually a really important hyperparameter, since um, actually it's kind of new as well, obviously. But there's a specific point when you do machine learning, or in the code rather, where the system recalculates the loss value and then adjusts the weights and biases, right? Remember, if we can remember back, you remember that we adjust the weights and biases to reduce loss. And it does that after each iteration. The batch size is the like number of examples it sees between each recalculation of loss and the weights. So yeah. So if we have a batch size of 6, the recalculation happens after every 6 examples. So every height, oh, why does loss end at about 3 or 1? Okay. So the reason why we will never hit 0 is because there's like, if you look at this thing, there's no perfect line to really calculate everything, right? So we'll never hit 0 because there's no straight line that will ever be able to perfectly hit all of these 12 values. And so there's always going to be a number that there'll always be this error in our model, but we can look past it, since overall it's a really good fit of the points, even if it's not perfect on all of them. So that's why it's always going to be higher than 0. We can look past it. So our batch size, this is mostly a parameter to help that helps define how fast our model will converge. So if we have a very small batch size, our model will take longer to converge. If we have a large batch size, will be faster to converge. It's kind of like, actually, yeah. So you can like try it out. So we have 0.5 of learning rate, 0.05 learning rate, and 100 epochs. So we can test out our batch size. I don't know, we can do 10. Or yeah, you can do this on your own. Try 10. And so our challenge is to minimize our batch size, I guess. Let's try 5. Yeah. So you could try 1 and it'll still work. So you might be asking, like, this seems pretty useless. Like, why does it really matter what your batch size is? It's important since when the model will look at these examples in batches, right? So if we take a batch of 1, it will look at that one value and then, adjust the weights and biases. But if you look at multiple at the same time, our model might be able to find patterns within those batches that it could then learn on and train on. So essentially, it's a way to kind of converge faster, which is essentially what we've been saying. But yeah, so we have so it kind of says it really best here. When you have very small batches, you might not have enough information to converge, but if you have a very large batch, you might have too much information for the model to really learn from. Kind of information overload. So yeah, that's what batch size is. And so those are, like, the 3 hyperparameters that you might be using.
So batch size is how many epochs it goes through before it decides whether or not to, like, change its learning rate and stuff.
No. So it's the amount of examples that it goes through before it changes the it's the number of examples it goes through before it changes the weights and biases. Does that make sense? So if you wanted to, here, you can, like.
So weights and biases, that's like the slope, right?
Yeah, those are the slopes.
Okay. Okay.
Yeah.
Wait, I thought an epoch was an iteration. So what is an epoch?
So an epoch is the model looking over the entire data set. So an epoch is when the model looks over all 12 examples.
Oh, okay.
And so when we say 100 epochs, it'll look over all 12 examples 100 times. That's what we're telling it to do.
Okay, so that's when the batch size is 12, right?
Wait, can you say that again?
So that's when the batch size is 12. Then it looks over the 12 examples 100 times.
No. So they're connected, but not connected in that way. So the batch size is, we'll look over like 12 examples and then change the weight and biases.
All right.
But the epoch is just telling it, look over the data set, the entire data set this many times.
Okay.
Does it make sense?
But if it's batch size 1, then it just looks over the one example 100 times.
No. Okay. So here's the key thing. Like, so the epochs have nothing to do with the actual calculation of the weights and biases. It's simply just a number to tell, hey, look at the data set this many times. The batch size is the value that actually determines how many examples we look at before we change or modify the weights and biases.
Okay.
So here. So it says here, one epoch spans sufficient iterations to process every example in the dataset. If the batch size is 12, then each epoch lasts one iteration. But if the batch size is 6, then the epoch consumes 2 iterations. And so if you had a batch size of 1, each epoch would be 12 iterations, which would mean 12 recalculations of the weights and biases. That's the connection between batch size and epoch.
Okay.
But the batch size doesn't determine how many epochs you have. I hope I didn't confuse you. Okay. So here's like a summary. So this is kind of how it would look. Our training loss should decrease steeply at first, and then more slowly until the slope of the curve reaches 0, which is when it converges. If the training doesn't converge for your current learning rate, you might want to train for more epochs. But if it is decreasing too slowly, you might want to increase your learning rate. If the training loss varies really wildly or oscillates, you want to decrease the learning rate. Lowering the learning rate or increasing the epochs or batch size is a good way to train or do stuff. It's a good rule of thumb. And then first you might want to try large batch sizes and then decrease until you see degradation. And then for real world data sets with a large amount of examples, your entire data set might not fit into memory. And so there you might want to decrease your batch size such that your batch can fit into memory. And so, as always, your hyperparameters are based on your data. So you always have to experiment and tune, that kind of stuff. So yeah, for these last 15 minutes, we'll essentially just do what we just did before, but now with an actual data set. So here's a data set on, so it's housing prices based on census data from California in 1990. And it's a good way to, do this stuff. So we have the data set, it's a CSV. And similar to, like I said before, CSVs are comma separated values. You have values that are separated by commas. And so these are the column names. And then these are the corresponding values in those columns, kind of like that. So yeah. So the next thing you can do is you want to load the data set into a training data set. And you can see that it does that. It does just that. And the next thing we can do is we can kind of examine what it looks like. So you can do training underscore df dot describe to get statistics of the data set. And so do you see any anomalies or any strange values in this data set? Yeah, I think I see one, which is the total rooms. I don't think there's supposed to be 1,000 rooms in your house, but maybe that's something different. Let's see. Yeah, so the maximum value is very high compared to other things. It's like the total rooms column. Yeah. So using like bad features like this might make your model also perform badly. So let's try some. So like, let's make a new function, or let's like redefine our build model and train model functions. So yeah, and then we'll also redefine our plotting functions as well. And so here, we can try running our model. Okay. So so we get this. And so while it doesn't seem like this doesn't really mean anything, right? Like, how is that a good fit? According to our root mean squared error, this is still an okay loss value. So we have 125, but you might want to get that closer to 50. Since I don't know if we can create a straight line that is able to calculate all of these, right? Okay. So what we can do now is we can define a predict house value, and then we can now use the model that we created here in here. So now we can kind of predict house values using our features and labels. And so I guess the question is this like a good predictor? Is the number of rooms? I think that's what it is. But do you think we accurately predict house values? if you compare label value and the predicted value, like are these similar? Yeah, so they're not accurate at all, right? So that means that our features aren't very good at predicting house values. So let's try something different. So we're going to try population next. So if you put in population, and then now you got to change these hyperparameters as well. So let's see. Let's try 5. And then 10. So you can like test it out and see whether you can find like a good place. Our learning rate is too high. I think that's what it's showing us. And try increasing this. So it does converge, which you can see by this this thing down here, how it's flat at the bottom. But when we compare our labels and our predicted values, they're nowhere near close. So I don't think that population produces any better predictions than total rooms, right? And so it's not useful. What we could try now is we could try okay, see what you wrote for the example. This one? No, in the solution. No. I wrote 0.05, 100, and 120. So unfortunately, it's still not very good. What we can do is we can try creating a synthetic feature. So let's try making our own thing. And this can be using we learned before. So we're going to try to make the ratio between total rooms and population. This is going to be really easy. You can do training _ df. And you can get total rooms and then divide that by training df dot population. And then you got to assign learning rates to all of these. So let's try 25. Batch size is 120. So I think if you played around with this more, you'd find that rooms per person is actually is a better synthetic feature overall compared to our previous total rooms and population, which is kind of amazing since even though these are bad features, combining them in a certain sense can make a really good feature. So, final thing is that we've tried like trial and error to find like good features, right? So instead, what we could do is we could try actually using statistics. So one thing that we could try is using what's called a correlation matrix. And this is what would allow us to find features that actually correlate really well to our labels. So here. When we do this, you can find that you can find all the correlations between the different values or the different like columns. And so, okay, so we have 3 minutes left in class. And I don't think we'll finish. But maybe for homework, you could do this last task, which is determine which of the 9 potential features would be the best candidate using this correlation matrix. And the final thing is I need you guys to do a survey. So please do this. I put it in chat. But once you finish that, class is over, and yeah, I think today was a little fast, but there's also a lot of stuff we had to do, which I guess is good. So once you're done with that survey, you're free to go. I think it's Julia, you could stay so I can help you with the thing.